Okay, in this video, we're going to look at section 2.3, dealing with techniques for computing limits. All right, so in this video, we'll talk about things like taking limits of linear functions. Also, we'll look at some of the laws of taking limits and do examples of those. Also, we'll look at limits of polynomial and rational functions, also one-sided limits. And we'll look at other techniques that are useful in calculating limits or evaluating limits. And also we'll look at the squeeze theorem to end this section. Okay, so here we got graphical and numerical techniques for estimating limits like those presented in the previous section provide intuition about limits. These techniques, however, occasionally lead to incorrect results. Therefore, we turn our attention to analytical methods for evaluating limits precisely. So here, we'll start off with the linear functions and how to find their limits. All right, for linear functions of the form f of x equal to mx plus b, the limit as x approaches a of f of x can be found by just doing direct substitution. Okay, so here's the theorem. Okay, so it's the limit as x approaches a of the function f of x. That's going to be equal to f of a equaling to m times a plus b. Okay, so that's the limit as we let x approach a of the function f of x. That just means we just substitute the x with a, and we'll end up with m times a plus b. So with that, with a linear function, we just do direct substitution. That's pretty much the easy one there. So in these examples here, let's say we want to evaluate the following limit, like in this case here, the limit as x approaches -2 of 7x plus 1. All right, in this case, all we do is just do the direct substitution because it is a linear function. So it'll be 7 times. We just substitute our x in 7x plus 1 with the -2. So it'll be 7 times -2 plus 1. And then 7 times -2 would be -14. -14 plus 1 is simply going to be -13. So that's pretty much the easiest one there. And then example 2. Let's say we got the limit as x approaches 6 of -9x plus 10. The limit as x approaches just approaches 6 of -9x plus 10. I realize that is a bit hard to see, but here it is. So to simplify that, we just substitute the x with 6. So this will be -9 times x, which is 6, plus 10. So here, -9 times 6 will be -54. -54 plus 10 ends up being -44. All right, next, the limit as x approaches 5 of 4x. The limit as x approaches 5 of 4x. And in this case, we just do 4 times, replace the x with 5, and that would give you 20. All right, now there is a note that the limit of any constant is a constant. So that means this: if I take the limit as x approaches whatever a is of that constant, it's just going to be that constant, because it doesn't matter where x is approaching. If I just have the limit of a constant, it's just going to be that constant. So like in this example, the limit as x approaches 5 of 6. That's just simply going to be 6, because it is a limit of a constant. Doesn't matter where x is approaching. If I have the limit of a constant, it is just going to be that constant. So the limit as x approaches 5 of 6 is 6. Okay. All right, now on the next page are the limit laws. So here, the following limit laws greatly simplify the evaluation of many of these limits. So here they are. There are 7 of them. We're assuming that the limit as x approaches a of f of x and the limit as x approaches a of g of x exist. The following properties hold where c is a number and m is greater than 0 and n is greater than 0 and they're integers. So like for the sum, which is number 1, if I take the limit of a sum f of x and g of x as x approaches a, that's going to be equal to the sum of their individual limits. The limit of f of x as x approaches a plus the limit of g of x as x approaches a. And then for the difference, if I take the limit of a difference as x approaches a of f and g, then that means that can be written as the difference of their individual limits as x approaches a. And then the third is the constant multiple. In this case here, the limit as x approaches a of some constant c times f of x. I can take this constant c, pull that on the outside, and then take the limit of f of x as x approaches a. Okay, also the product for limits. If I take a limit of a product of f and g as x approaches a, that's the same as taking the product of the individual limits. So the limit of a product is the same as taking the product of their individual limits as x approaches a. And now for the quotient, if I take the limit of f of x divided by g of x as x approaches a, here I can write that as the quotient of their individual limits in the numerator and the denominator. The provision there is that g of x, the limit as x approaches a of g of x, cannot be equal to 0. So here your denominator cannot be equal to 0 when you apply the limit law for quotients. Now for power, when you're doing the limit of f of x and s raised to the n as x approaches a, here's what I can do. I can take the limit of f of x as x approaches a and raise that to the power of n. And then the last one is a fractional power, where we have the limit of f of x raised to the n over m power as x approaches a. Here I can do the same thing for the power rule. We're taking the limit of f of x as x approaches a, and whatever that is, it's going to be raised to the power of n over m. The provision here is that your f of x has to be greater than or equal to 0 for x near a, and if m is even and n over m is reduced to lowest terms. Your m has to be to an even number, has to be an even number. N over m must be in lowest terms. Okay. Now in law 7, where we have the limit of f of x to the n over m. That involves the mth root, that's the denominator, of f of x, where x is near a. And if the fraction n over m is in lowest terms and m is even, this root is undefined unless f of x is non-negative for all x near a. Okay. Now you have to recall that to take the even roots of a number, for example, the square roots or the fourth roots, the number must be non-negative if we want the result to be real. Okay. Because if you try to take the square root or the fourth root of a negative number, you're not going to get a real number from it. Okay. Now we're going to apply those limit laws that I just showed you with these examples, like in example 5. Let's say I want to compute the following limit, assuming the limit as x approaches 2 of f of x is equal to 6. And we're going to state the limit laws used to justify the computation. Like in this one, the limit as x approaches 2 of 2 times f of x. Well, notice I got a constant in front of the f of x. What I can do is pull that constant in front of the limit. So here I'm going to be using the constant multiple law for limits. So I have 2 times the limit as x approaches 2 of the function f of x. Okay. If you recall, the constant multiple rule states that if I have the limit of a constant times some function f of x as x approaches a, that constant can be pulled in front of that limit. So this is what I just did here. I'll pull the 2 in front of the limit as x approaches 2 of f of x. So here I'm going to say I use the constant multiple rule. And now I'm given that the limit as x approaches 2 of f of x is equal to 6. So I can say 2 times and just substitute the limit as x approaches 2 of f of x with what is equal to, that's 6. So here 2 times 6 will be 12. And that will be the final answer to that problem. Okay. All right, next example would be to assume that the limit as x approaches 8 of f of x is equal to 27, and the limit as x approaches 8 of h of x is equal to 3. Here we're going to compute the following limit and state the limit laws used to justify the computations. So here we've got the limit as x approaches 8 of f of x divided by h of x. All right, so here we got the limit of a quotient, because we got a numerator and a denominator. The limit of a quotient, I can write that as the quotient of their individual limits. So here I'm using the quotient law for limits. That's this. So here I'm going to write that as the limit as x approaches 8 of f of x divided by the limit as x approaches 8 of h of x. Okay. So here I'm applying the quotient law. So now the limit as x approaches 8 of f of x, that's given to be 27. That will be divided by the limit as x approaches 8 of h of x, that's given to be 3. So 27 divided by 3 is 9. So the limit as x approaches 8 of f of x divided by h of x will be 9. All right, here's the next example. Here we're assuming that the limit as x approaches 9 of f of x is equal to 14, and the limit as x approaches 9 of g of x is equal to 3. And I want to find the limit as x approaches 9 of f of x minus g of x. Well, notice that the limit of the difference of f and g, I can write that as the difference of the individual limits here. So I can write this as the limit as x approaches 9 of f of x minus the limit as x approaches 9 of g of x. So here, I'm using what they call the difference law. The difference law. Well, the limit as x approaches 9 of f of x, that's 14, minus the limit as x approaches 9 of g of x, that's going to be 3. So 14 minus 3 is 11. So that's what the limit as x approaches 9 of f of x minus g of x will be. All right, now let's try this example here. The limit as x approaches 4 of f of x is equal to 13. The limit as x approaches 4 of g of x is equal to 5, and the limit as x approaches 4 of h of x is equal to 4. And here we want to compute this. The limit as x approaches 4 of f of x divided by g of x minus h of x. Okay, well, notice we got a numerator and a denominator. So let's start off by using the quotient law. Well, we're going to do the limit as x approaches 4 of the numerator, f of x, divided by, and then the denominator. In the denominator, we're going to do the limit as x approaches 4 of g of x minus h of x. So here we're using the quotient law. Because I have the limit of the quotient, I can write that as the quotient of their individual limits. Okay, now in the denominator, I've got the limit of the difference. I can write that as the difference of the individual limits here. So let me bring down the limit as x approaches 4 of f of x. And that's divided by, and I'll write this as the difference of the individual limit. So it'll be the limit as x approaches 4 of g of x minus the limit as x approaches 4 of h of x. Now this is where we're using the difference law. All right. Now the next line is just doing the substitution here. The limit as x approaches 4 of g of x, that's going to be, of f of x, that's just going to be 13. So the 13 will be in the numerator divided by the limit as x approaches 4 of g of x, that's given to be 5, minus the limit as x approaches 4 of h of x, that's 4. So now if I simplify this, 5 minus 4 will be 1, and then 13 divided by 1 ends up being 13. So the limit as x approaches 4 of f of x divided by g of x minus h of x will end up being 13. That's the final answer. All right, let's do one more of these. Well, let's look at one more of these. We're going to assume that the limit as x approaches 7 of f of x is 7, and the limit as x approaches 7 of g of x is equal to 3. And I want to compute this. The limit as x approaches 7 of the cube root of f of x times g of x plus 6. Okay, this is what I'm going to do here. First of all, I'm going to write the cube root of this in its equivalent exponential form. So the cube root of f of x times g of x plus 6 underneath that radical. Let me bring over the limit as x approaches 7. And I'm going to rewrite this as f of x times g of x plus 6. And that's going to be raised to the 1/3 power because it is the cube root. So the cube root of something in exponential form will be to the 1/3 power. So what's in the bracket is going to be to the 1/3 power. Now I'm going to use, and in this case, let me do this. Since it's to the 1/3 power, I can do this. Use the fractional power rule and do this. Take the limit as x approaches 7 of f of x. I need to put this in bracket as well, times g of x plus 6. And all of that would be to the 1/3 power. Okay, because according to the fractional power, if I have a limit of something to that power, then that means the limit of this, whatever that is, will be to the 1/3 power. Okay, so this goes back to that fractional power rule or law. All right, now let's focus on what's inside this bracket right here. I'm going to use a combination of two different rules, the product rule and the sum. Because notice I got the limit of a product that can be written as the product of their individual limits. And the sum, the limit of a sum can be written as the sum of their individual limits. All right, so this is what I'm going to have in the bracket. The limit as x approaches 7 of f of x times the limit as x approaches 7 of g of x plus the limit as x approaches 7 of 6. All of this will be to the 1/3 power. And I might as well write that I use the fractional power rule here on this line. And on this line, I use the product and sum laws. So here I use a combination of the two. Because I got the limit of a product that can be written as the product of their individual limits. The limit of a sum can be written as the sum of their individual limits. Now let's simplify these. The limit as x approaches 7 of f of x, that is 7, times the limit as x approaches 7 of g of x, that is 3. Now for the limit as x approaches 7 of 6, if you recall, the limit of any constant, regardless of where x is approaching, the limit of a constant is that constant. So the limit of 6 as x approaches 7 is going to be 6. And all of this is to the 1/3 power. All right, so now let's simplify this. 7 times 3 is 21. 21 plus 6 is 27. So I have 27 to the 1/3 power. Now, if I want to write that in radical form, this will be the cube root of 27. And the cube root of 27 would be something like this. What power what number to the third power would give you 27? Has to be 3. So the final answer there would be 3. Okay. So that's how we use those limit laws to evaluate or compute limits. Now let's talk about polynomial and rational functions. As in the case of linear functions, the limits of a polynomial function can be found by direct substitution. That is, the limit as x approaches a of p of x is equal to p of a. You just substitute the x with the value of a. Now, the limits of rational functions are also evaluated by direct substitution as long as the values of the denominator is not 0. Okay, so here for polynomial functions, the limit as x approaches a of some p of x function will be p of a. We just do the direct substitution. Now, for rational functions, we do the same thing. We substitute the numerator with the a value and the denominator with the a value. But the provision there, the restriction there is that q of a cannot be equal to 0. That means your denominator, when you after you substitute your x with whatever a is, you can't have a 0 in the denominator. Now, in this example here, let's say I want to evaluate the following limit. Here I got the limit as x approaches 2 of 3x cubed minus 3x squared plus 4x plus 7. Well, as you can see here, I do have a polynomial function, which means I can just do direct substitution. So I just substitute each x in that function with 2. So that means here, I will have 3 times, x will be 2, so it'll be 2 cubed minus 3 times, x is 2, so it'll be 2 squared, plus 4 times, the x is 2, plus 7. So all I did there was just substitute each x with 2, okay? Because since it's a limit of a polynomial function, as x approaches some value 2, we just do the direct substitution in our polynomial functions and simplify. So 3 times 2 to the third is 2 times 2 times 2, that's 8, minus 3 times 2 squared, that's 4, plus 4 times 2, that's 8, plus 7. Well, 3 times 8, that's 24, minus 3 times 4, that's 12, plus 8, plus 7. Now, 24 minus 12, that will be 12, plus 8 will be 20. 20 plus 7 would be 27. So the limit as x approaches 2 of 3x cubed minus 3x squared plus 4x plus 7 will end up being 27. Okay. Right, here's another example. Let's say I want to evaluate this limit. The limit as x approaches negative 4, 4x squared plus 8x minus 4 divided by 6x minus 4. And in this case here, if I substitute x with a negative 4, I'm not going to get a 0 in the denominator. Okay, and if you want to check to see what value of x that would give you a 0 in the denominator, you can do this. I'll take that denominator, 6x minus 4, set that equal to 0, and solve for x. And by the way, this is a rational function to be exact, because you have a numerator and a denominator, and you do have a variable in the denominator. So now when we solve for x, we add 4. That means I get 6x is equal to 4. Divide both sides by 6, x will be equal to 4, 6 reduces to 2/3. Okay, and we're taking the limit as x approaches negative 4. So we know we're not going to get a 0 in the denominator. Only time you get a 0 in the denominator is when x is equal to 2/3. So in this case here, we can do the direct substitution. So let's just go ahead and substitute each x in this function with -4. So it'll be 4 times x, which is -4, and that's squared, plus 8 times -4 minus 4. All divided by 6 times x, that's -4 minus 4. So all I did there was just substitute each and every x with -4. Now, all we have to do there is just simplify. Let's see. I'm going to bring over the 4. Square -4, that's -4 times -4, that's 16. Minus 8 times 4 would be 32. And by the way, plus 8 times that -4 makes that a minus 32, then minus 4. All divided by 6 times -4 will be -24. Minus 4. Let's see. 4 times 16 is 64. 64 minus 32 will be 32. 32 minus 4 would be 28. And -24 minus 4 would be -28. So -28 divided, well, 28 divided by -28 ends up being -1. Now, of course, you can use your calculator to calculate all of this, both the numerator and the denominator. All right, example 12 is this. Here we got a square root in the denominator. So if I want to evaluate the following limit, in this one, the limit as b approaches 6 of 3b divided by the square root of 4b minus 25 minus 1. All right. I could do this. Take that denominator of the square root of 4b minus 25 minus 1. Set that equal to 0 to see if b is the same as this limit that I'm taking as b approaches 6. If it's not, I can use direct substitution. So if I add 1 to both sides, that means the square root of 4b minus 25 would be equal to 1. And then to get rid of that square root, I would square both sides of this equation. That would mean 4b minus 25 is equal to 1. Add 25 to both sides. You'll get 4b is equal to 26. Yeah. 4b is equal to 26. I'm sorry. This should be plus. And that means I need to subtract 25 on both sides. I copied the problem wrong. So it'd be -24 when I do 1 minus 25. So 4b will be equal to -24, and that will mean b will have to be equal to -6, which is different from what I'm taking the limit for as b approaches 6. So those two are different. So I can apply direct substitution to this problem. So here, I just substitute the b with 6. So this will be 3 times 6 in the numerator divided by the square root of 4 times b, which is 6, plus 25 minus 1. Let's simplify this. 3 times 6 will be 18. That's going to be divided by the square root of 4 times 6 is 24. 24 plus 25 would be 49. Then I got that minus 1 outside the radical. Now I can take the square root of 49. That will be 7. And then 7 minus 1 will be 6. And then 18 divided by 6 ends up being 3. So the limit as b approaches 6 of 3b divided by the square root of 4b plus 25 minus 1 ends up being 3. Okay. All right, next we're going to look at one-sided limits. Now in the last section, we did talk about one-sided limits on the last video that I did. All right, theorem 2.2, limit laws 1 through 6 and theorem 2.4 also hold for left-sided and right-sided limits. In other words, these laws remain valid if we replace the limit as x approaches a with the limit as x approaches a from the right or the limit as x approaches a from the left. Okay. So if you remember those one-sided limits, limit as x approaches a from the right, and also limit as x approaches a from the left. Okay. Law 7 has to be modified slightly for one-sided limits, as indicated in this box below here for the fractional power limits here. If I have the limit as x approaches a from the right of f of x to the n over m, that would be this here. The provision for that would be that f of x is greater than or equal to 0 for x near a, with x being greater than a, because we're talking about our right-sided limit. A from the right means that x has to be greater than a. If m is even and n over m is reduced to the lowest terms. And then for this second one, the limit as x approaches a from the left of f of x raised to the n over m, that will be the limit as x approaches a from the left of f of x raised to the n over m. The provision there that f of x is greater than or equal to 0 for x near a, with x being less than a, because it is a left-sided limit. Anything on the left side has to be less than a. If m is even and n over m is reduced to the lowest terms. All right, so if we look at this example dealing with one-sided limits, is a piecewise function. The f of x is equal to 6 minus x if your x value is less than 4, and x over 2 plus 3 if your x is greater than 4. That's a piecewise function. Here I want to find the limit as x approaches 4 from the right and the limit as x approaches 4 from the left. And then part B, does the limit as x approaches 4, that function exists? If so, what is it? And if not, why not? All right, let's start by answering part A. So in this case here, I need to find the limit as x approaches 4 from the right for that function f of x. All right, now let's think about this for a moment. You can draw a number line, and here's 4. If we're coming from the right of 4, that means our x values are going to be greater than 4. So that means anything greater than 4, we use this function, x over 2 plus 3. So here we're dealing with the limit as x approaches 4 from the right of x over 2 plus 3. And the reason why we're using x over 2 plus 3, because anything to the right of 4, it would take in the limit as x approaches 4 from the right. Anything to the right of 4 has to be greater than 4. So that's why we're using x over 2 plus 3 here. Now we can do direct substitution here. Just do 4, substitute the x with 4, now b over 2, plus 3. 4 divided by 2 would be 2. 2 plus 3 is 5. So the limit as x approaches 4 from the right for the function f of x will be 5. The other part is the limit as x approaches 4 from the left. This time we're coming from the left of 4. We're going in this direction. That means your x values must be less than 4. And if your x values are less than 4, we must use this expression, 6 minus x. So here the limit as x approaches 4 from the left, that would be the 6 minus x. And here your x is going to be 4, so that'd be 6 minus 4 ends up being 2. So as we approach 4 from the left, this function would be 2. Now, answering part B. Does the limit as x approaches 4 of the function f of x exist? Take a look at the values that we came up with, okay? The limit has to exist if the limit as x approaches 4 on the right equals the limit as x approaches 4 on the left. You can see those are two totally different values here. So the answer there will be no. And that is because the limit as x approaches 4 to the right of f of x is not the same as the limit as x approaches 4 from the left of f of x. Okay, the limit as x approaches 4 from the right is 5 for 4, and the limit as x approaches 4 from the left of that function is 2. They're not the same. So that limit does not exist as we approach that x approach 4. Okay. So far, we've been doing direct substitution with these limits here. There are other techniques. Let's say we get a 0 in the denominator when you do direct substitution. When that happens, you might need to replace the limit of a function with an equivalent one that can be evaluated by direct substitution. So one or two things can be used. We can factor and cancel, or pretty much saying divide out any common factors that you have, or you can use what they call conjugates. And we're going to look at one or two examples where there are conjugates being used here. All right, so let's start with this example here. Evaluate the following limit. Let's take the limit as x approaches -8 of x squared minus 64 divided by x plus 8. Now, I'm going to show you what happens when you use direct substitution. So if I was to just use direct substitution by substituting the x with -8 in the numerator and in the denominator, you'll see -8 and u squared will be 64. And then -8 plus 8, that's 0. 64 minus 64 is 0. Notice I have a 0 over 0. And I do have a 0 in the denominator. And by the way, 0 divided by 0, we call that indeterminate form. Excuse me. Indeterminate form. 0 divided by 0. And since we produce a 0 in the denominator, we're going to have to try writing this in a different way so that we can evaluate this using direct substitution. All right, in this case here, I'm going to need to use factor this, because I know x squared minus 64 is in this case a difference of 2 squares. So we're going to use that. Okay. So I'm going to bring over the limit as x approaches -8. And I'm going to factor x squared minus 64. That's a difference of 2 squares. I can factor that out with x and x for the x squared. One number times itself gives me 64, has to be 8. And of course, one has to be plus, the other one has to be minus, all divided by x plus 8. So as you can see here, I can divide out the common factors of x plus 8. And I will be left with the limit as x approaches -8 of x minus 8. Now here I can use direct substitution with this. I can substitute this x with -8. I will have -8 minus 8, or -8 plus -8, which is -16. Okay. So this is just an example where you may have to divide out common factors, first factor it out, and then divide out those common factors, and then take the limit. Okay. Here's another example. Say we got the limit as x approaches 4 of x squared minus 3x minus 4 divided by x minus 4. Well, if I try to do direct substitution, I know I'm going to get a 0 in that denominator, because 4 minus 4 does give me 0. So I know I'm going to need to try to factor this and divide out the common factors here. So, of course, the limit as x approaches 4, that x squared minus 3x minus 4. I'm going to try to factor that out into 2 binomials here. I'll bring over x minus 4. Now, in this case here, x squared breaks up as x and x, and I need factors of -4 that would give me a -3x. Well, I know 4 and 1, but of course, the larger of the two factors will take the sign of the middle term. So the 4 has to be a minus, the last term has to be plus. So the limit as x approaches 4 will be x minus 4 times x plus 1 divided by x minus 4. And here I can divide out those x minus 4s. They're gone. Now, I have the limit as x approaches 4 of x plus 1. And now I can apply direct substitution by substituting the x with 4, so it'll be 4 plus 1, ends up being 5. So that means the limit as x approaches 4 of x squared minus 3x minus 4 divided by x minus 4 ends up being 5. All right, let's say we had this. The limit as x approaches 5 of x squared minus 25 divided by 5 minus x. In this case, we're going to get a 0 in the denominator if we use direct substitution. So that means we need to try to factor and divide out any common terms here that we might have. All right, so let's see what we got. That x squared minus 25, I can factor that out into a sum and the difference of the same two terms, since I have the differences of two perfect squares. All right, that x squared minus 25 breaks up as x and x. 5 times 5 gives me 25. One has to be plus, the other one has to be minus. Okay. And you might have to go back to some of your algebra to see why I factored it out like that. That is a difference of two squares. the denominator has 5 minus x. And if I want that to be x minus 5 or x plus 5, what I need to do here is factor out a -1. When I do that, the minus x becomes a positive x. The 5 becomes minus 5. And notice in this case here, I can divide out the x minus 5. So in this case here, I have the limit as x approaches 5 of x plus 5 divided by -1. Now I can apply direct substitution by substituting the x with 5. So it'll be 5 plus 5 divided by -1. 5 plus 5 is 10. 10 divided by -1 ends up being -10. So the limit as x approaches 5 of x squared minus 25 divided by 5 minus x is equal to -10. Okay. All right, number 17, example 17. Here I want to evaluate this. The limit as h approaches 0 of 4 over 7 plus h minus 4/7, the whole thing divided by h. All right. I know I'm going to get a 0 in the denominator. And notice in this case, I have an expression that has fractions in it. So what I need to do here is I'm going to put this h over 1 in the denominator. I need something that's called the LCD of these secondary fractions here that I have. 7 plus h, 7, and 1. Well, I got a 7 plus h, and I have a 7. So I'm just going to combine those as 7 times parentheses 7 plus h. That's my LCD. And now, this is what I'm going to do. I'm going to bring over the limit as h approaches 0 of, here I'm going to multiply each and every term in this expression by that LCD of 7 times 7 plus h. So for the 4 over 7 plus h, it's going to be multiplied by 7 times 7 plus h. And then minus 4 over 7, it's going to be multiplied by 7 times 7 plus h. Oh, that's going to be divided by the h itself would be multiplied by 7 times 7 plus h. All right, next I'm going to bring down the limit as h approaches 0. I'm going to simplify what's inside this bracket. This term right here where I got 4 over 7 plus h times 7 plus h. The 7 plus h's divide out. And I'm going to be left with 4 times 7. That'll be 28. And then minus, but there's 4 7s times 7 plus h. These 7s divide out. So I'm going to be left with 4 times parentheses 7 plus h. And the denominator, this right here, h times 7 times the quantity 7 plus h. I'm going to do this 7 times h, that's 7h. And then I'm going to leave the 7 plus h on the outside. Okay, because I'm not going to simplify what's in that denominator. All right, now let's simplify what's in the numerator. I'm going to bring down the limit as h approaches 0 of the numerator, that's 28. If I distribute that minus 4 over the 7 plus h, this will be minus 4 times 7, which is minus 28. And then minus 4 times the plus h will be minus 4h, all divided by 7h times the quantity 7 plus h. All right, next I'm going to bring down the limit as h approaches 0. Notice I haven't taken the limit yet, so I have to keep bringing this expression down the limit as h approaches 0. And then 28 minus 28, that zeroes out. You're left with negative 4h divided by 7h times the quantity 7 plus h. And you see why I didn't simplify this in the denominator, because here I can divide out the h's. So now we got the limit as h approaches 0 of negative 4 over 7 times 7 plus h in the parentheses. Okay. Now, I'm not going to get a 0 in the denominator, so I can go ahead and take that limit. Here, this h will go to 0. Then this expression will be this, negative 4 times 7 times 7 plus 0. Then negative 4 over 7 times 7. And if I simplify this will be negative 4 over 49. And that will be the final answer for the limit as h approaches 0 of 4 divided by 7 plus h minus 4 sevens all divided by h, negative 4 over 49. Now keep in mind, in this problem, all I did was just the only thing I did at the end was take the limit. Everything else was algebra. Everything else was just plain algebra. Okay, that's something you're going to have to be very familiar with. It's just the algebra. How do you do the algebraic part before you start taking the limit? All right, here's another one. Let's say I want to evaluate the limit of the square root of x and minus 14 divided by x minus 196 as x approaches 196. Obviously, I will get a 0 in the denominator. Okay. So in this case, I'm going to need to do something here. Notice I got the square root of x and then minus 14 in the radical. I'm going to be using what they call conjugates. And what I mean by that is this. If I take I'm going to work with the numerator here because I got that square root of x. If I have the conjugate of the square root of x minus 14, that conjugate is going to be this. These are the same two numbers. Only thing different here is the sign. It changes to the opposite. That subtraction changes to addition here. And if it was addition, then it will change to subtraction. So the conjugate of the square root of x minus 14 would be the square root of x plus 14. This is your conjugate of this number, of this expression. So what I'm going to do here is multiply the numerator and the denominator by that conjugate. That's what I'm going to do here. And it would be best if I just write it like this. So limit as x approaches 196 of square root of x minus 14 over x minus 196 times the conjugate for the numerator and the denominator. All right. So now the limit as x approaches 196. Now you're going to see why I multiply by the conjugate, because this is what you do. You have the sum and the difference of the same two terms. What you do there is square the first term, the square root of x times the square root of x. Well, if you take the square root of something and you multiply it by itself, it eliminates the radical. You'll be left with what's underneath it. It's just going to be x. And then minus the square of the second term. 14 times 14, that would be 196. Okay. And then the denominator is going to be, I have x minus 196 times square root of x, and then plus 14. And notice x minus 196 in the numerator, and in the denominator that divides out, you will be left with the limit as x approaches 196 of, you have a 1 in the numerator, the denominator will be the square root of x plus 14. And I'm not going to get a 0 in the denominator, so I can use direct substitution here. So that means I'll have 1 over, I'll substitute the x with 196, so it'll be the square root of 196 and then plus 14. So it'll be 1 over, if I take the square root of 196 in the calculator, I will get 14. So here, 14 plus 14 will be 28. So I'll end up with 1 over 28. So the limit as x approaches 196 of the square root of x minus 14 divided by x minus 196 will end up being 1 over 28. Okay. All right, let's look at a couple of more of these. Here's example 19. He'll want to evaluate this limit. In this case here, the limit as x approaches 46 of x minus 46 divided by the square root of x minus the square root of 46. All right, in this case here, notice my denominator, square root of x minus square root of 46. Again, I'm going to use conjugates here. The conjugate of the square root of x minus the square root of 46, well, it's the same two terms. The only thing that's going to be different is the sign. It's a minus here, so its conjugate would be plus. So it's the square root of x plus the square root of 46. And here I'm going to take that x minus 46 divided by the square root of x minus the square root of 46 and multiply it by its by its conjugate in the numerator and in the denominator. So now if I take the limit as x approaches 46 of, well, the numerator will just remain as x minus 46, and I'll put that in parentheses, times the square root of x plus the square root of 46. The denominator, I'm multiplying by conjugate, so that means I square the first term and then minus the square of the second term. The square root of x, and you square it, will just be x, wipes out the radical. Minus the square root of 46, and you square that, it also wipes out the radical, so it'll be x minus 46 in the denominator. And notice I can divide out the x minus 46s, they're gone. That would mean I will have a limit as x approaches 46 of the square root of x plus the square root of 46. Well, I don't have anything in the denominator, so that means I can do direct substitution here for this limit. So I can just go ahead and directly substitute the x with the 46. So it'll be the square root of 46 times the square root of 46. And how many square roots of 46 do I have? I got 2 of them. So it'd just be 2 square root of 46. And that's all there is to it. So here at the end, all I did there was just took the limit. Everything else I did before it is algebra. Okay, here's one more of these. Let's say we got the square root, the limit is h approaches 0 of the square root of 25 plus h minus 5, all divided by h. Okay. Start by writing the limit as h approaches 0 of, here we need the conjugate of the square root of 25 plus h and then minus 5. So the conjugate of that would be, of course, the square root of 25 plus h, change the minus to a plus, and then 5. That would be our conjugate. So what we're going to do here is take that expression of the square root of 25 plus h minus 5, all divided by h, and multiply it by its conjugate in the numerator and in the denominator. So now I got the limit as h approaches 0 of, notice I have conjugates in the numerator and the denominator. One's minus, the other one is plus. So I can do this, square the first term, square root of 25 plus h, and you square that, it's going to wipe out the radical. So you'll be left with 25 plus h, and then minus 5 times 5, or 5 squared, that'd be 25. So when you're multiplying conjugates, it's always going to be the square of the first term minus the square of the second term. And then the denominator, I'm just going to leave as is. It'll be h times, and in parentheses, the square root of 25 plus h, and then plus 5. Now I'm going to bring down the limit as h approaches 0. Haven't taken the limit yet. I need to simplify what's in here first, and then we'll take the limit. 25 minus 25, that's gone. So that means I'm going to have h divided by h times the quantity of the square root of 25 plus h plus 5. And also those h's divide out. I'll be left with a limit as h approaches 0 of 1 over the square root of 25 plus h plus 5. Okay. Now I'm not going to get a 0 in the denominator, so I can go ahead and take the limit of this. So that means I'm going to have 1 over the square root of 25 plus 0, and then plus 5. And then 25 plus 0 is 25. So I have the square root of 25 plus 5, and the square root of 25 is 5. So 5 plus 5 will give me 10. So my final answer there will be 1/10. So the limit as h approaches 0, the square root of 25 plus h minus 5 divided by h will end up being 1/10. And finally, you got the squeeze theorem. Sometimes it's called the pinching theorem or the sandwich theorem. Okay, now here's the theorem for that. We're assuming that the functions f, g, and h satisfy this. F of x is less than g of x and less than h of x. That means g of x is greater than f of x and greater than or equal to f of x and less than or equal to h of x for the values of x near a, except possibly at a. If the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x, they both equal to some value L, then by the squeeze theorem, the limit of g of x as x approaches a must also go to L, since g of x is in between f of x and h of x. Now we're going to apply that squeeze theorem to a couple of examples like this one. So let's say I want to answer parts A through C. Okay. And in part A, it says here, it's a statement, negative absolute value of x is less than x times the sine of 9 over x and less than or equal to x, absolute value of x, true for all x not equal to 0. So I want to know, is x times the sine of 9 over x greater than or equal to the negative absolute value of x and less than or equal to the absolute value of x true for all x not equal to 0? As long as this denominator is not 0, then that statement will be true. All right, now part B. Let's illustrate this inequality with a graph. Okay, and in the homework, you're going to be given a choice of graphs to pick. So I'm going to enter this in the calculator. By the way, on the left, the negative absolute value of x is f of x. Your g of x is the one in the middle. X times the sine of 9 of x, 9 over x, and then absolute value of x is h of x. And I'm going to put all three of these in the calculator, so you can see what this is. Okay. I'm going to go to y equal to and clear out all the junk that's in my calculator. In y1, I'm going to put f of x here. Negative absolute value of x. Well, the negative key is at the very bottom, so you'll press that. For absolute value, you have to press the math key. Use your right arrow key to go to number, the number menu. The first menu item is absolute value, ABS. Select number 1. And then I'm going to enter the xt, press xt theta for the x. I'm going to use my right arrow key to get out of that absolute value. Use my down arrow key to enter this part that's in y2 for y2. X times the sine of 9 over x. Well, for the x, we press xt theta for the x. For the sine, there's a button that says sin for sine, and then gives you the left parentheses. Then we do 9 divided by x, close parentheses. Now I'm going to enter h of x in y3, which is the absolute value of x. In this case here, we press the math key, go to the number menu, NUM, select number 1 for ABS, which is absolute value, and then get your x by pressing xt theta in. Okay. I'm going to check on something here. I'm going to press this mode key because I want to make sure that radian is highlighted. One time I did this, the degree was highlighted and I didn't get the right graph. You want to make sure radian is highlighted because you're dealing with a sine function, sine of 9 over x. So make sure that is highlighted. Okay. If it's not, use your down arrow key to put the cursor over radian and press enter to highlight it. Okay. Now I'm going to do second and mode to quit. Then I'm going to go to graph. Okay. Now they do give you dimensions here to use here, from -9 to 9, and then from -9 to 9 on the X. So if you want to, you can do, press the window key. For X min, that's going to be -9. Down arrow key to X max will be 9. And I'm going to leave the X scale at 1. And then this is for Y. Your Y min would be -9. Y max will be 9. Y scale remains at 1. Then press graph. That's the first one, absolute value, negative absolute value of X. This one is for Y is equal to, X times sine of 9X, 9 over X. And the other one at the top is the absolute value of X. That's what the graph looks like. So you just have to select which one of these that you see here fits this. And as you can see here, it's going to be this answer choice right here. Okay. Now, that's part B. Part C is using the squeeze theorem to find the limit as X approaches 0 of X times 9 over X. Well, let's do this. I need to find the limit as X approaches 0 of negative absolute value of X, which is the function on the left of the less than or equal to. And I had to find the limit of the function on the right side that less than or equal to, which is that limit as X approaches 0 of absolute value of X. And if they're approaching the same place, or the same value, then this limit of X times sine of 9 over X as X approaches 0 must approach that same value. All right, as X approaches 0, negative absolute value of X will go to 0, because I can do direct substitution here by just saying this. Bring the negative sign over, substitute the X with 0. Absolute value of 0, but 0 is neither positive nor negative, so it will be 0. What about the limit as X approaches 0, the absolute value of X? Again, replace the X with 0. Absolute value of 0 is 0. So if this is f of X, that's going to 0. And if this is h of X, if that's going to 0, then that means the limit right here, based on the squeeze theorem, the limit as X approaches 0 of X times sine of 9 over X must go to 0, based on that squeeze theorem. Because the limit of the function on the left and the limit of the function on the right, they're both going to 0, then the one in the middle has to go to 0. All right, here's another example of using that squeeze theorem. Let's say in part A, we want to illustrate the inequality of 1 minus X squared over 6 is less than sine of X over X and less than 1 for X near 0 on the graph. And I want to choose the graph below. Well, let's enter these in the calculator. So this 1 minus X squared over 6, that's f of X. The sine X over X, that's g of X. And of course, 1 h of X. And of course, we're doing this near 0 on the graph. So let's go to y equal 2 and clear these equations out. In y1, I'm going to put 1 minus x squared over 6. So this will be 1 minus x, and then hit your x squared button, divided by 6. Go down to y2. We're going to enter this sine of x over x. So we have to press the sine button right here, sine of x, get the x, close parentheses, divided by x c theta n for your x. And then for y3, it's just 1. Okay. And I think they give you some dimensions here that you can use here for your window. So I'm going to press window. X min would be -4. X max would be 4. The x scale will remain at 1. But these are for your y's here, -2 to 2. Y min will be -2. Y max will be 2. The y scale will remain at 1. Then we press graph. The one on the bottom that you saw was 1 over x squared minus 6. The one here is that g of x being sine of x over x, and then the one for h of x will be 1. Okay, so we're going to pick one of these that fits this. And it looks like that first graph right here. Okay. Okay, so that's what that graph looks like. Now we're going to find the following limits here. Let's find the limit as x approaches 0 of 1 minus the x squared over 6. Well, if you look at that, that's pretty much you're not going to get a 0 in the denominator with the 0. So I would use direct substitution here. Just directly substitute your x with 0. So this will be 1 minus 0 squared over 6. This will be 0. 0 squared is 0, divided by 6 is 0. 1 minus 0 is 1. So the limit as x approaches 0 of 1 minus x squared over 6 would be 1. And then the limit as x approaches 0 of 1. Well, the limit of a constant is a constant. So that's going to be 1 as well. Okay. So from these limits that we got for the one for the left function and for the right function, the one in the middle, it's got to be going to the same value. So limit as x approaches 0 of sine of x divided by x has to be equal to 1 based on the squeeze theorem. Okay. So that does conclude this video on section 2.3 dealing with techniques for computing limits. Now, again, you're more than welcome to email me if you have any questions about anything presented in this video or anything that's in the homework on my math lab.